then U0. Okay, I think this is what we are trying to prove. And we are very close to finish the proof. Okay, I don't want to erase this because we will use it, but let me recall the following. In particular, we have this corollary. If you want U2 solutions of dt of ui, let me make it our life simple, u, 2k, u, k, an integer, positive. And suppose that u1, u2 belongs to the continuous in hs of Rn. Suppose that s is larger than n half, maybe more than 1. If then you're saying, suppose that they have two solutions regular enough of some semilinear problem, such that when I take the different, the equation satisfied by the difference of these two, I can put it in this setting. We are not saying anything fancy, because what you are trying to apply is this theorem to the difference of these two solutions. At time 0, you have this. At time 1, you have this. Then you have that they are equal. Question. Suppose that you put one of these two solutions to be 0. Do you know any solution of this equation that decay Gaussian at 2 times? This is a known. Any superlinear decay of solution of this, for me at least, is unknown. You have this theorem. Is this theorem sharp? That's not clear. Suppose you have two solutions of this problem. Suppose that you take u sub 2 to be 0. Then you are saying, if I have a solution of this problem, because you are taking u2 to be 0, that decay Gaussian at 2 times with this, you are 0. But is Gaussian necessary? I mean, do you need power 2? Can you have power 1 plus epsilon, power 4/3? I mean, any power in between? This is unknown. And what is annoying is for the KdV, this is not unknown. I mean, this is the same theorem is known and is sharp. For the Schrödinger equation, for a strange reason, is unknown. Then we don't know how close we are from this theorem. Okay, this is an open question. How far is this sharp? Put it yourself in the simple situation, u2 equal to 0. Is this sharp? Okay. This is a question that I want to leave in your hand. Okay. Of course, I mean, there were a few things that we reduced. We don't have to have the same gamma at 2 times. I mean, we can have alpha and beta, and we reduce that. Also, some remarks before we go to the last things that we did improve last time. Where do we use this hypothesis? Suppose that you go back and you say, where are you using this hypothesis? We use this hypothesis to prove that if you have Gaussian decay at time 0, a Gaussian decay at time 1, and you satisfy this, you have Gaussian decay in the middle. How do you prove this? We prove a lemma that say if you satisfy there exists epsilon such that if the potential be in L infinity and you satisfy this equation, and you have, if this is true, and this is true, and f multiplied by this belongs to L1 of 0T1 L2, then you are in L. This is bounded. Doesn't matter too much how you bound this. Okay. The theorem says if you have this problem where the external force have the decay that you need, the potential is small, then you have that if you decay Gaussian in the middle, you decay Gaussian if you decay Gaussian in the extremal, you decay Gaussian with the same exponent in between, right? And okay. Then how you apply this theorem if you are in this situation? What do you do? How you apply this theorem? I mentioned this, but I don't know if that was correct. To apply this, because if we go to the proof that we did last time, we are assuming all the time that this is finite. And we have only this at 2 times, and we have this. This is our hypothesis. Then what do? You say, you write your equation in this form. Maybe I have to put L1 here. This is what you really need. Okay, what do? You write this part. You rewrite this in this way. This part that is supported at infinity, the ball of the complement of the ball of center 0 multiplied by u plus this. This is going to be your external force. This is going to be your potential now. Why this potential is as small as you need here? Because you have this hypothesis. Is that correct? Why this external force satisfy? Right? I mean, the only thing that you know is that W. The only thing that you know is that W is in between is that it's L2. How do you know that this function multiplied by the Gaussian is integrable? What is the support of this? Compact support. Is it in this ball? Then everything is bounded by the exponential of r squared. Huge r, doesn't matter, but this is finite. Then you have it. You can apply this result. You adapt this to prove from the beginning that if you have this exponential decay in between, you have it in the middle. Okay? We are using that several times in our proof, and I mentioned this, but I don't know if that was clear enough. Okay. Is this clear? Where is this hypothesis? How this hypothesis is used? We prove this lemma with all the pain. This is the lemma that have Calderon projection, and then we make it for the linear, and then we do this. That was a key lemma, okay? Also, we proved this Kalman estimate last time. Okay, what was? We proved this Kalman estimate Last time we proved this, Klainerman. We proved this. If G it has compact support, I have to put n plus 1. I'm sorry, I have to put n plus 1 because you have compact support in n plus 1. And that phi is this function, mu x plus rt1 minus t square e1 square minus 1 plus epsilon r squared t1 minus t 16 mu. Okay? We proved this. And then the proof of the main theorem was to truncate the business to apply to G in the interval this. Okay, what is the only thing that remains to have a proof according to what we say? Well, we need to, the last thing that we have to prove is this lemma. There exists n such that this estimate holds. Plus this is less than n exponential of n dv and L infinity, and n is going to depend on the mu and the okay, and this is the supremum of the L2 norm everywhere plus j equal to 0 to 1. What happened with the exponential weight? J L2. Okay. This is the last thing that we need to prove. You remember that we did use this, and how we use this? Well, we truncate the business such that we never reach 0, 1, then we don't need to put that one there, and we control this. This is important matter. Why this is important matter to have control over the gradient? Because when you truncate here, right, this G that you need to apply to this G, you need to have compact support in this interval. Right? Then you have to, your U is going to be, your G is going to be your U, something that caught in X, something that caught in T. So this was a mu M, and this was T of M and T of R. Okay, then when you introduce this, you don't satisfy this equation, you have extra term. And one of the extra terms is going to appear the gradient of here. When you apply Laplacian here, when the Laplacian of this is here, then you're okay. But when you start to split the one derivative here, then you start to be in trouble. You have to control the gradient. But you are okay because this is exactly what gives you the control of the gradient. And this is okay because you are far from the boundary. This is a bad estimate close to the boundary. When t is equal to 0, t equal to 1, you don't get anything, but this is not what you have. This part here gives you the form. Okay, then we have to prove that. If we prove that, we are okay. Okay? Then let's prove that. Then we don't need this. We don't need this remark. We don't need Klainerman. We're going to prove this lemma. And this n may depend on this gamma. Let's prove this. Well, proof. You call f to be exponential of x squared u. And remember that u is your solution of this business here. Okay, what is the equation that f satisfies? F satisfies this equation. So, by the argument that f satisfies this equation, where S is the symmetric bar okay, let me call this for the moment phi of xt. Gradient plus Laplacian plus gamma t, and A is equal to this. Okay, let's do it from the beginning with the right. Let's make it shorter. Let's put what we have here, and that's it. This is this. We're going to make it in one step. Then S is going to be equal to minus I gamma 2. The gradient of this is going to be another 2. Then it's going to be 4x sub j dj of this operator. Let's write it like this, x, right? Plus Laplacian of this is going to be 2n. And mu A is going to be I Laplacian plus gamma, the gradient of this. Okay, what is the gradient of this? Is 2x mu is going to be 4. Okay, let's see if this is correct. 4. Okay, let's check this is correct. I'm going to start from. Okay, let's check our computation. Then we want to know what f satisfies. You have this. Then you say dt of, you apply dt I you apply this operator dt minus I Laplacian plus b of x t of applied to u is 0 is equal to apply all this operator dt of minus I Laplacian of b of x t applied to exponential of minus f equal to 0, right? Okay. Then the derivatives in t doesn't introduce any problem. This is going to be derivatives in t. Then we have I. Then we have the Laplacian of this. The Laplacian of this is going to be this one. Then you have when the gradient hit here and the gradient hit here. If the gradient hit here is minus twice x, and if the gradient here is this. Is this correct? Then I have to apply the Laplacian of this. When the Laplacian hit here, I have this. When the Laplacian here, I have 2, because it's twice the derivatives, and then I have another 2 coming here, then it's going to be 4. And now I have the Laplacian of this. Okay, what is the Laplacian of this? It's going to be minus twice c x sub j e minus x squared. Then if I take another derivative, it will give you minus twice a. If I give another derivative, it will give you plus this. Then this is going to give you minus 2cn. I'm going to put this outside. Because you are adding this with this n time. You have dj, xj. And then you have this. This is going to be 4 x squared, is that okay? Plus bf equal to 0. Okay, this is the equation that f satisfies. All this multiplied by f, by the way. Is this okay? Okay, let's see if I have that correct. The derivative in this here, then Laplacian is here to the other side. This is okay. Then I have this one. It's going to be plus in this side, but I pass to the other side. It's going to be minus. Then it's 4x mu gradient. It's okay. I have this one. Then I have plus 2 mu gamma. Is that gamma? 2 gamma n multiplied by I, that is plus, but I pass to the other side. It is here. Then this one is with a minus, but you pass to the other side is then is I minus. Is that plus or minus? That is the only one. I have it plus. It's a minus in this side. When you pass to the other side, it's a plus. Then it's okay. We satisfy that. Is this okay? Is this okay that this is the equation that f satisfies? Okay, it's a simple computation. Please. I'm sorry? Is gamma squared? Okay. It's okay? Yes, because it came out twice down. Yes, perfect. Yeah, it should be gamma squared. Okay, we're going to do this computation several times, maybe next, okay? What is the, and then we have to compute dt, ds, s of A. Okay. Let's accept that this is equal to this. Okay, this is a problem. I put this. This is the twice the identity. This is x, twice the identity. Okay, let's do it because it's not going to look. Well, let's leave it up to here, and we will do the commutator in a moment. Okay, let's forget that. The order is not going to matter at all. Okay. In some moment you will see that we have to compute the commutator. Okay. Claim 1. If H is the L square nor L2 square of this, and D is the symmetric power applied to F multiplied by F, then the second derivative of H is equal to twice the first derivative of the real part of this. Let's prove that, because this have nothing to, this is an abstract business here, plus 2 dt of S plus S F A F F plus let's prove this. This is very similar to some computation that we did when we were trying to prove for some linear problem that has to do with the hard DL2 version that this quantity was logarithmically convex. Okay? But now we are not proving that. We are proving something else. Okay, let's prove this estimate. Okay, this is very general argument, in fact, and then we will go here and so forth and so forth. Okay. Okay, who is proof? Who is H prime of T? Is equal to dt of F plus F dt of F. That is equal to twice the real part of this quantity. Because this one is the conjugate of this, right? By convenience, you write this way. dt of F minus S of F minus A of F, F. And if I have to have equality, what do I have to add? I mean, if I want to say that this is equal to this, plus twice SF multiplied by F. Remember that this is 0. This A is skew symmetric. And this is symmetric. Therefore, this part that you are adding here is 0. This is a negative 1, you put that. This number, this is symmetric, you don't have to put the real part. Is this correct? Okay. This is the derivative of H. This is twice, if you want, d of t. Okay. Who is the derivative of d of t? You want to write it like this. This is derivative with respect to t of this term. Then this is equal. When the derivative hits the operator, you have this. Then you have this part. And then you have this part. And this is equal to dt of f. This operator is symmetric. You can put here. And this is, then you have this plus this. Okay, let's do it carefully. This is exactly equal to this. This quantity plus its conjugate is equal to twice the real part of this. That this is equal to this dt of f minus a of f st of f plus twice the real part of a of f s of f. Right? I erase, and I put minus here, and I have to put the same business plus. Okay, I'm trying to get to the formula. Why this formula? Well, this formula is very similar to the one that we did for the proof that something was logarithmically convex and is related with the Klainerman estimate. Let's do this part here, separated, because it's... Then you have the real part, twice the real part of AF SF. Therefore, this is exactly equal to AF SF plus the conjugate of this. That means that is equal to this, right? The conjugate of this is to switch. Therefore, this is equal. If I change S to this side, I have exactly the same business because S is symmetric. If I switch A to this side, I have minus. Then what you have here is the commutator. And you need all the time the commutator because this is what gives you what you want. Okay? Then all this is equal. This go with this. Then this is st of s plus the commutator. All this apply to f. Then you have this term and this term together. Plus twice the real part of this, right? Okay. Then let's write the following. Twice the real part of any expression you have twice the real part of x multiplied by y is equal to, it's called polarization, x plus y squared minus x minus y squared. Then you're going to pick up the double product here, and here the double product, you have 4 times the same business, you have 1/2. This is called polarization, right? Therefore, this part that you have here is 1/2 of the addition of these two minus 1/2 of the subtraction. Are you with me? Therefore, who is the second derivative of h? Well, the second derivative of h is the derivative of this first term real part of dt of f minus a of f minus f of f plus twice the derivatives of this. But twice the derivatives of this is twice all this. And this is what you want to prove. Okay, this is exactly what you want to prove. In fact, you keep going, you can prove that this function is logarithmically convex if you put some exponent there. But that's not, I mean, we are trying to do the minimum to finish our proof. Okay. We proved that. Okay? Now, any question that we prove the first claim? Okay. No question with the polarization, nothing? Yes. Okay, now let's go to the proof of the business. Okay. What are we going to do? These are inner product in X. We are in L2 in X and time. Therefore, we are going to multiply by this quantity and integrate by part. So then we're going to multiply by T1 minus T, this inequality, this identity, star, and integrate by part. Then by part. Integration by part. Okay. Then what are we going to have? This part doesn't have derivatives. Then let's leave that there. Then we're going to have twice integral between 0 and 1, t multiplied by 1 minus t, the inner product between this operator applied to f multiplied by f. This is the integral in x. This is the integral in t. Okay? And this is this one. This is going to be less or equal to what? This one plus this one, if I pass with a minus to the other side, this one I pass to the other side. This one I leave it there. And I try to bound this one. Then I have to stay with only one of these two. Then this pass to the other side, and we have less or equal. Plus integral between 0 and 1, t, 1 minus t, multiplied by this norm. then since I want to estimate this one from above, I can remove this part that is positive. Okay, then I have this estimate. Is this okay? This one? Okay, now let's do this integration by part here and here. Then the integration by part between t1 minus t h double prime t dt is t1 minus t h prime of t for t between 0 and 1 minus the derivative goes to the other side, that is when the derivative hit here is 1 minus 2t h prime. This is 0 because t equal, okay? Then this is equal, you integrate by part again. This is going to be minus 1 minus 2t h of t evaluated in 0 and 1. And then you have a minus here. The derivative is going to give you another minus. But the formula gives you another minus. You have 3 minus. Then you have, I think it's this one. Then the derivatives of that give you 2 h of t dt. Let's see if this is correct. Okay. And this one, that part give you, when you evaluate in 1, give you minus plus. When you evaluate in 0, give you this. And then you have this. Then all this, the first term is less than h of 0 plus h of 1 plus minus twice the integral between 0 and 1 h of t dt. Is this okay? Then I did the first integration by part. Let's do this one. The integral between 0 and 1, t, 1 minus t, derivatives with respect to t of the real part of all this, dt, what you have there, is equal to t, 1 minus t, real part of this, in t equal to 0, t equal to 1. That die because you are in 0 and 1. And then you pass the derivatives to the other side, is going to give you minus the derivatives of this, that is 0, 1, 1 minus 2t, real part of this product. But since you have a minus here, this is going to give you plus twice the integral between 0 and 1, the real part of dt of f minus f. And now, plus what you have here. Okay, we have this formula. This bound this. This is bounded by this quantity. I can remove this because this is positive. Are you with me if I remove this? You can remove this because this is positive. Okay, H is the L2 norm of F. Okay, now let's write who is this, each of these. This is this is the norm of F at 0, L2 squared, plus the norm of F at 1, L2 squared, plus who is all this? Who is dt of f minus the operator a applied to f minus s applied to f? Well, it's equal to b multiplied by f. You can put absolute value, the real part, and so forth. This is going to be less than the integral between 0 and 1, the L infinity norm. You want to be very picky. the L infinity norm in a space. And now you have F multiplied by F. Okay, you have F L2 squared dt. It is okay. I took the L infinity. This is equal to IBF. I put absolute values inside, forget the real part, and then have this. And this one is exactly the same business. This is plus integral between 0 and 1, t, 1 minus t. All this is equal to IBF. Therefore, you have B in L infinity squared multiplied by the F of t squared dt. Therefore, you have bound. This is the bound of this quantity. We have this. Remember that you can B is in L infinity. The L2 norm of F is the L2 norm of this expression. And because we are in this setting, the L2 norm in the full interval of this quantity is going to be bound by this quantity plus this quantity by a huge constant that depends on the truncation. Okay, let me write all this. Then I don't need the claim, I only need these two. Okay, let's go here. Who is this? F in L2 is this, at time 0. F at type 1 is this. This is something that we know that is bounded in the whole domain, if you wish. This part, we know that we can control the L2 norm of this quantity by controlling what happened in 0 and what happened in 1. Is this okay? Remember that according to the lemma that I raised, if you truncate this at infinity and 0, you can bound anything that happened. Then everything that you have here is bounded in terms of this and this. All this is bounded in terms of this, this, and this. Is this okay? Because we prove a lemma that says that you can truncate this part, and then you say what happened between 1 and 0 is controlled what happened exactly at the point 0 and the point 1, and we have. Then we only need to prove that this quantity controls this. This and this. Okay, this is an expression that depends on what happened at the time 0, at the time 1, what happened in the L2. This is some constant that depends on all your mu and so forth. Okay, then the only thing that remains is to prove that this, it remains to show, to see that this quantity is larger than these two. This plus this is, let's call this one A1, this is called A2. This is larger than A1, A2. This is all that remains to prove. Are you with me? Because this left-hand side of this inequality is something that depends on the data. Okay. Any question up to now? Okay, now let's compute who is this operator. Who is this? We have this. Who is dt s commute with A? Well, if you take derivative with respect to t, here you have nothing because there is nothing that depends on t. And this guy is out. This is simple. Then we have s applied to A minus A applied to s. Let's see what do we get. Okay, this is multiplication, this is multiplication. We don't have to commute these two. Therefore, this is going to be, since you have minus I here, and you have I, and you're going to apply both of them, what you have is this for x sub j dj commuted with the Laplacian dk. This is this commute with this. This commute with this. It will be 4 this is 4, and then you have another 4 here, then it's going to be 4 squared gamma cube of this one, x sub j dj applied to this one, x sub k squared. This commute with this. This commute with this. This commute with this. This is a constant commute with this. This is a constant commute with this. This is the two guys that you have to do. Is this clear? The commutator reduced. This is a constant commute with any of this. Therefore, this commute with this. Okay, let's see this one first. This one, okay, then you have this. You have x sub j dj of dx squared of f minus, multiplied by f, if you want, minus the other way around, dx squared x sub j dj of f. That's what you have. Then you have the 4 and so forth. Okay, what happened in this part? When these two derivatives hit here, you have nothing. Is that okay? When this one derivative hit here, when these two derivatives hit here, is exactly what you have here. Therefore, the only thing that you're going to pick up is minus twice one derivative here, delta xj, one derivative here, dj dk of f. This is what you get. And this is equal to minus twice. Then this is only applied when these two are equal. Then you have twice dx dx. Okay, and you have summation. Okay. Then this is twice gradient of dj of f, dk of f conjugate. Okay. This part here is equal to, if you want to write it, is minus twice dx dx. Okay, and you know what you mean for that is that. Okay, let's do this part. Then we have x sub j dj of x sub k square of f multiplied by f conjugate minus x k square x sub j dj of f. Okay. Then this derivative has two pieces. When the derivative hit here is exactly what you have here, then you have to have the other part. Then when this derivative hit here, it's the only thing that remains. Then you have 2xj xk f of f. No. Wait. This is twice. What is the derivative of this? Is xk delta kj f f. Is this okay? Because when the derivative hit x sub j, then you will with 2xk multiplied by this. Therefore, what you have here, and this is exactly equal to write this twice. This have to be equal. Then it's x squared f squared. Right? Therefore, what you have, you can write it there, is equal to plus. Okay, this one is minus twice dk dk. Of course, you have this here. And this one is 2 times multiplication by x. And then you have, of course, plus 4 phi cubed. Therefore, the commutator, at the end of the day, you have all this quantity is larger. You have this. St plus S A of f multiplied by f is larger than 8 gamma gradient of f squared plus, then you have 4 squared here, 32 gamma cube x squared over f squared. Okay, this quantity is more than this. Okay? Is any question? See, they start to, the gradient appear and the weight appear, but they appear in the f. Now we have to translate everything to the u, because we want this estimate in u, not the f. Okay? The painting have not finished. Okay? Any question? Okay, now let's remember that what we want is to control the u, not the. Okay. This is 2, 1, 2, 3, 4, 5. Okay. Okay. Claim 1. The gradient of f squared plus 4 times this quantity, f squared dx is larger, or is equal, in fact, to this. Okay, let's prove that. Because we want the estimate in u, not in f. Still, we know that the only thing that we need is to do this bound estimate. Okay, let's write what is this. Proof of the claim. Who is this? This is the gradient of this expression. And this is equal to this. The gradient of this. Okay, then since we put one, okay, let's write that carefully. What do we have? This is equal. If I put the derivative here, it's exactly what I want. This will be when the derivative hit here is this. Let me write it carefully. This is, not to use this notation, this is this multiplied by his conjugate. Since we are doing everything in a painful way, we have to do this. This is conjugate dx. Okay, let's go. Okay, then we have the possibility that this hit here and this hit there. Therefore, you have, this is exactly equal to, when you write it, you have this. This is when the derivative hit here and the derivative hit here. Now you have to go when one derivative hit in you and the other one hit in the other side. Then you are going to have that this one, suppose that this one hit here. This is going to be twice u x sub j. And then you're going to have the same power here than there. Then you have u here and this one hit here. Okay. And the other way around. When this then you have with one derivative hit the exponential and the other one hit u, and you have the two possibilities there. And then you have finally the one when both of them hit the exponential. Then if both of them hit the exponential, we're going to have 2 mu x sub j, right? Then it's going to be 2 through x sub j squared e squared u squared dx. Okay, let's see, you have twice this multiplied by this, right? And then this is 4 squared, and you add this, you have this. Are you with me? Okay. Sorry, this is okay, this is the derivatives of u times conjugate, then integrate by parts here once, right? If you integrate by part here once, you're going to have if I integrate by here once, what do I have? I'm going to have this all is going to be minus, when this derivative hit here, you're going to have twice this and twice this one. This one, u conjugate dx. That is exactly what you just got there. And minus, you have when this derivative hit this one. dj xj. Therefore, this part cancels this. And you finish with what? This one, that is what you have there. This one, this is adding in J that gives you N. Then you have this quantity. Then you have proof that this is equal to this. Okay? You don't need any of this. Okay, we proved claim 1. Any question with the claim 1? No question? Okay, claim 2 is the Heisenberg inequality. That is a big number for something very simple. Is this. Is this one, that the gradient of f squared plus 4 rho okay. Do I need to put a square here? Yes, I need to put the square here. No. Let's see. Let's be careful because I only use this part. Let's be careful with the constant because I think that okay, I only using this one. When you have this part, you have when one derivative hit here, you have this, and the other derivative hit there. You have this one, you integrate by part. You have 4, and you have. I'm not using this part. I'm missing a constant. I mean, this is too good to be true. This is I'm missing a constant. Okay. 2j, 4. 2j, derivatives of j. Then these derivatives give me n, these derivatives. Okay, I know what is. Okay, what is the error here? When this derivative hit here is exactly what I have here. Right? This is the derivatives of this. When this derivative hit here, what is you go down? This is a 2 here, and there is another 2. Okay? This derivative is going to hit this term. Then what is exactly the expression that will come out? Now you have these 2 and this 2. Then this is going to be the come out. Then you have this one that you have here. It's not that this one cancels this. It's that this one that you have here is minus 8, this x squared what I have here is only 4. Then in order to cancel this one, I need to add another 4. Okay? Then you have to be careful with the derivatives of this is 4. Then you have minus a here, plus 4, but you have plus 4. Then this one with this one with this one cancels. Right? And then you only finish with this part and this part. You have now okay. Is that clear? That what is it? When you take derivative here, we forgot to put the 2 that is here. Therefore, this part, you have 4 positive here, and you have 4 positive that help you in this side. Cancel the 8 that you have. and then you finish only with this term that gives you positive and this one that gives you negative. Okay. Is now okay? Is now okay? Okay. This is getting long, but okay, claim 1, claim 2. This is true. Okay, why this is the, let's prove this. Okay, this is the following. N multiplied by the L2 norm of a function is exactly equal to d. Suppose that you are f multiplied by f. If you integrate by part, this is dj minus dj of f conjugate minus xj f dj f conjugate, and this is less than, this is the inner product between x and the gradient, then this is less than x f in L2, gradient of f in L2. Here you have twice, right? Then you have proof that this quantity is less than this. This is the Heisenberg inequality. And now you write multiplied by 2 gamma n here is less or equal to 4 gamma xf square ff square. If we want to have this, then we just say that this is equal to twice 2 mu epsilon square xf square plus 1 over epsilon square gradient of f square, right? I use A multiplied by B. I use that A multiplied by B twice is less than A squared plus B squared. Therefore, if you want to get this, you accommodate your business. You take, what do you want? You want this to be 1. Therefore, you need that 2 gamma over epsilon squared to be 1. Then this is equal to gradient of f squared. And then you have epsilon squared is equal to 2 gamma. Then you have 4 gamma squared f of x squared. Okay? Is this okay? Okay, then we prove that. This is Heisenberg. Okay. Therefore, you have that and you have this together. Claim 2 is this one. Is larger or equal to this f. But who is f? F is this one, right? F. Write this with the definition of f is this one. You have this. You have this. This is what you prove. I translate this into F equal to this. This is what we just proved at the beginning. Then if you add both of them, you have twice this business here. The X is larger or equal to this one. Therefore, since this estimate was larger than this, you can take a piece of it, this one, you take a piece of this one to get this. And what do? The other piece is trivial because you put the definition of F here. Then you take a piece of this, you take half of this. This is larger than, there is a square here. Then you take 4 mu multiplied by this one, maybe 2 here. You put 2 a square. Then you have 4 and another 4 here. I have this. Right? Plus, I forget this piece and I put this piece here. Then I put A of this, 4 of this I took. I took 4, 8, and 2. Then 4, 16. Then I still have a piece, 16 of this. Okay? I forgot a piece of it. The first part, give me this. This part, give me this, maybe with a 2 mu in front. 2 gamma. This part. This part gives me 16 square, and I put the definition. Now you multiply by t, 1 minus t in both sides, and integrate in t, and you have what you want. Multiply by t, 1 minus t, and integrate dt, then you get exactly what you want. You're going to say, but you don't have 1 here and 1 here. Well, take the minimum of the 2 and pass to the other side. Okay? Therefore, you have seen that you control this one, multiply by t, 1 minus t, this. That is exactly the L2 norm of what you want. And you control this one, that is exactly this term. Then you have proof. Well, that was a long proof. I'm sorry, but you can see that this is, in the moment that you see estimate with gradient and x, you see that you have control over the function itself. It's a matter of working with the Heisenberg. Any question? Then we prove the theorem. Now we have, if we put this in the right order, we have everything proved. Rigorous and justify and everything. Okay? And this was a key argument because before proving this, we need to put this function here and to have some control over the gradient because we didn't know how to control the gradient. You need to have some weak control over the gradient to be able to truncate and control the business. Any question? Okay, to finish this, and we will state what we will do next week. Let's forget about the nonlinear problem that we don't know if this is sharp or not. And ask yourself a simple question. Is this sharp? Can you construct solution of, can you give me a potential that satisfy this and satisfy this such that it have Gaussian decay and it's not zero? Can you have solution of this problem that have Gaussian decay? I mean, it's any way, any trick that you can cook some potential. I mean, you don't have to be so sophisticated. You can say, I want to be sure that this is not empty. The theorem is not empty. There exist solutions, there exist potentials satisfying this hypothesis. Above hypothesis, such that, and data, and solution, such that the equation start have solution with the Gaussian decay. Solutions at t equal to 0, t equal to 1 with Gaussian decay. Forget about for the moment that we want sharpness or not. You are trying to, the question is this class empty? Do you understand the question? I mean, well, let's say that this is a very simple trick and very unfair, but this is what it is. And by the way, this is not, there was Carlos Kenny giving a talk on this, and who is Monica Bizan's boyfriend? Kilip. And Kilip gave us the example. Okay, this example was given by Kilip. It's not our example. Okay, let's make it simple. Take B, instead of B a function of x and t, just be a function of x. In fact, with Gaussian decay. It's a function that depends only of x with Gaussian decay. You don't need many of these things, but just to make it simple. With Gaussian decay. If you want, take it a Gaussian. Then solve this problem. This is a parabolic problem. With Gaussian decay, the data with Gaussian decay. Then what is the solution of this? If you want to write this using Duhamel principle, is convolution with the Gauss kernel by the initial data plus the integral between 0 and t, the Duhamel business, b of x, w of t prime, dt prime. Okay, these have Gaussian decay. And this is convolution with Gaussian. You convolve to things that have Gaussian decay, These have Gaussian decay. Then you don't need to prove that this one has Gaussian decay. This is an L2 will do it. This have Gaussian decay, this have Gaussian decay, then these have Gaussian decay. In fact, you want real to simplify your life. You don't need this to have Gaussian decay. You can prove it that is from here by iteration, but to make it shorter. Now, what do you do now? Solve this problem. With the same potential, and I put the initial data is going to be the solution of this problem, W of x at the time epsilon, for epsilon positive. Any epsilon you want positive. Your initial data is going to be the solution of this problem at time epsilon. Then what is exactly this? Then u of xt is e to the I write this in this way. The solution of that is equal to this. This is a group. You perturb by something bounded, this generates a group. You have all the right to write this in this way. The solution of this can be written in this way. But this data here is solution of this problem. And in fact, W of t by the same token can be written like t Laplacian plus b of x u sub 0, W0. Therefore, this is exactly, this one is solution of this. This is e to the I Laplacian plus b of x t e to the Laplacian with an epsilon because it's at the time epsilon plus b of x W of 0. Then at the time 1, this have Gaussian decay. Therefore, u at the time 1 is just e. This is going to be, put 1 here. And this is exactly equal to this. One plus I, epsilon Laplacian plus b of x of W0 of x. Or if you wish, u at the point 1 is exactly I plus epsilon Laplacian of W0, that is the u sub 0 of x plus 0t ui plus epsilon Laplacian t minus t prime b of x, right? U t prime, t prime. Therefore, this have Gaussian decay, this have a piece that is real, this have a Gaussian decay, this have a Gaussian decay, this have a Gaussian decay, everything have a Gaussian decay. Or you write it like this, and you can see that this is have Gaussian decay. You write it like this, it's simple. Then at t equal to 1, this is convolution. What is the Fourier in the side of the Fourier transform? What you see. This part gives you oscillation, but this part gives you the Gaussian decay. Then you can write this kernel with a, okay, you just have to take the Fourier transform of this. Okay, the Fourier transform of this, you have Gaussian decay. These have Gaussian decay, these have Gaussian decay, these have Gaussian decay, these have Gaussian decay, then everything has Gaussian decay. Therefore, you have solution that have Gaussian decay. You just have to solve this in the heat equation and put your initial data solution of that. And of course, if you put things to the pen of t, then you don't have such a nice trick that you can write the group and the semi-group in this way, and they commute and so forth. I mean, you can write it like this, or this is over. It's over. Okay. Any question? Okay, that finished the... Oh, I'm sorry, I erased the... Okay, let's see what is the first thing that we will prove next week. We're going to have theorem of this source, but now we are going to be global in time. Okay, and the first theorem we will prove will be this one. Okay, let's take the first theorem to see that we are going to... Okay, theorem, next week, we will start proving this theorem, and all these proofs are much simple. Next week. You will see that all these proofs are much simpler than this one. Okay. Suppose that you have a solution of this one. Suppose that you that belong to the continuous in 0 infinity in L2 of R n solution of this the same equation that you have before. Suppose that the potential B is real. This is a big difference. We are not assuming real there. Why do you want to assume that this is real? Because if this potential is real, you preserve the L2 norm. You only need this to say that the L2 norm of your solution is constant. When you multiply by u, conjugate here, and conjugate here, you integrate by part, this part disappears. Real. Okay, this is the only thing that you need that. Suppose that B can be written in two ways. You can split B in two pieces. And for the time being, suppose that B2 is not a big deal, but let's write both of them for the moment. You have that B1 of xt, both real valued, real valued. Suppose that B have this decay. Suppose that B2 is supported in outside the unit ball for all t. Is supported in the x, y, such that x is always more than 1. Suppose also that the negative part of the radial derivatives of b2 of x of t, this boring thing I will explain why decay like cx to alpha. Then there exists a lambda 0 that may depend of c1 that you put there, C2 that you put here, and the L infinity norm of your potential. Such that if the supremum for T positive of the L2 norm with this weight is finite for P equal to 4 minus 2 alpha over 3, then U is 0. Okay, let's try to understand this statement. You're saying, let's forget for the moment that this guy is there. Suppose that you don't have that. This guy is not there. This guy is not there. Suppose that you have a potential. Suppose the potential is just bounded. Alpha is equal to 0. Then if alpha is equal to 0, you cannot have a solution that belongs for all time to decay here for third. Okay, remarks. Suppose that alpha is equal to 0, p is equal to 4/3. If alpha is equal to 1/2, then you're going to have that p will be like p. Alpha is 1/2, then this is 1. It's like p will be almost 1. But this is not true. I mean, you need a little bit. Okay, this is extremal case. Okay. Let me see that in particular we prove the following. Okay, let's suppose that we have a solution. Suppose W that belongs to H1 of Rn is a solution of the elliptic problem. Satisfy this elliptic problem. W plus this potential x is equal to 0. Is that okay? Suppose that you have a solution of this. Suppose that that B is L infinity. Not necessarily real valued. Is this solution a solution? Do you satisfy this? Do you satisfy this equation? This W that doesn't depend of t, satisfy this equation. Is satisfy this one? Yes, because the derivative is in t0, this is 0. Right? Then you satisfy this same equation. Do you preserve the L2 norm of this? Right? The t doesn't pay any attention to that. You preserve the L2 norm. Then you can apply this theorem, because this theorem says that, the only thing that you need is to preserve the L2. Then what are you saying? That you apply the theorem and say, if you have a solution of this elliptic problem that the potential is bounded, you cannot decay more than p equal to 4/3. And this is mesh co-resolve. You recover mesh co-resolve. Then, if this is mesh co-resolve. And we recover mesh co-resolve. Yes, the only thing that we use for real valued is that you preserve the L2 norm. It's the only thing that we will use. But you preserve the L2 norm of this solution because it's time independent.
So you can replace the real values?
Yeah. You will see that in the proof. It's the only thing that we use is this. Then mesh co-results say that if you have this with any constant that you want, we prove it with some, you don't need all the constant. If you surpass some constant, then you have to be 0. And he proved that if you have complex value potential, this 4/3 is the best possible. In particular, we recover this elliptic problem that is not part of our business whatsoever, right? And forcer is sharp. You have solution of this problem that decay like exponential to power 4/3. If this is complex valued. The open question is, if this is real valued, everything should be, this number here is not 4/3, is 1 plus epsilon. If the potential is real, this should be 1. But for us, we are going to be able to prove this theorem by corollary of this. And we are going to prove some application of that result to the Schrödinger equation. Okay, the semi-linear Schrödinger equation. Okay, next time we will prove this theorem, and you will see that the arguments are somehow similar and simple than what we use today. Okay, we will start from here next week.